Hello and welcome back to the lab. Today on the bench is something a little more low-tech than normal. We have a Homemedics kind of white noise maker. Typically, we use this in the bedroom to help go to sleep, and it does a thunderstorm ocean, a brook, summer night, which is crickets and a few other things, rain, and then just some standard white noise. We have a 15, 30, and 60-minute timer, and we have an on-off and a volume control button. It's been acting up for quite some time, and it now needs to meet the bench of healing. So my initial thoughts on this is, one, when I take it apart, I got to clean it up. I have changed the batteries. This particular one we got... I don't remember how we got this. We did not buy this new, so I don't have the power supply that goes with it. It can be run off of a 6-volt, 300 milliamp power supply into the DC jack, but I do not have that, so we're running it on 4 AA's at the moment. They last a reasonably long time, so nothing major there. No corrosion on the batteries or anything like that, so... Contacts are good, and it is a fresh set of batteries, so we don't have a generic power problem. What's going on is we'll turn it on, and of course now that it's camera shy, right there, so it's turned off again. Now I can hear it, and now it's off, on, off. So I'm going to take a look at the capacitors, see if anything needs to be replaced. Obviously, that's one of my first, given the age of this thing, and it's a consumer electronic probably from the early 90s. I think you can actually still buy these new, but obviously capacitors are suspect number one. I also need to service this control, so this volume knob. The switch is working, but the volume knob is not. There, now it's deciding to work. This is what it sounds like. So now the volume knob decides to work. So obviously this control needs to be serviced and replaced if necessary, probably just serviced. But other than that, we'll look at the caps to see if there's any other problems. But let's crack it open. Okay, we had 4 self-tapping screws into plastic, which is never a good sign for serviceability or longevity. At least we can get in. It's not sonically welded or anything like that. We'll pop the batteries out. There we go. And well, that's relatively simple. But that control is not. Oh. So this is the... the lines aren't long enough. This control is the potentiometer that I'm curious about, and there's the snap action for the switch on and off, which is a very interesting mechanism in a modern piece of equipment. I wouldn't expect an exposed switch, but definitely like this solder joint's a little dry. Definitely some serviceability stuff there. One more screw. We'll get the board loose. And then we'll need to... Well, we need to, yeah, probably. Oh no, I need 2 more screws to get the board loose. Might not need to pull the knob. But let's see. Three more screws to get the board loose. That one was hiding in there. All right. Nope, we don't need to pull the knob. Okay. This transistor has some stuff on it. We got 2 caps, and then we have a blobbed micro under here. That's probably where all the magic is happening. That's a very interesting control. Definitely not normal. Okay, while I'm waiting for some things to flash off from cleaning, the knob was disgusting. So I got the knob cleaned up. I also looked up this IC. So our command and control is here underneath this blob. This IC is the power amplifier. We have a 10 microfarad 25 volt cap and a 220 microfarad 10 volt cap. So I will probably have those in the lab, so I will go ahead and replace those. And I will actually try to do that on camera. One thing to note, if you're ever taking a look at a lab and you're curious what soldering iron tips people end up using, take a look at their tip storage. By looking at the tips, you can tell which ones get the most use. Not this one. That's actually probably my second most used tip in the lab. And you can tell it's got all kinds of oxidation and discoloration. This is my most used tip in the lab. That's not a conical. That's a very small wedge tip. And then this is I need to chassis solder or work on really big 12 volt amps. That was the last time he came out. I had to fix some car amplifiers and do some 12 volt stuff, and the pads were just enormous. Well, forgive me if the fume extractor comes in on the video. I really try not to solder without it anymore. As long as I can help it. Okay. Negative is towards the switch. See what we can do without getting burned. Doing this around the camera is entertaining. What is the stuff that's on these parts? Oh, I pulled the wrong lead. Oops. It's this one. I have to move the camera over to the other side next time because it is all kinds of in the way of the irons. Okay, after making sure the polarity is correct, which is negative side going over towards the control, and also making sure we have an appropriate clearance on the part, we'll go ahead and put this in place. Also touch up the part we desoldered accidentally. And get a little more solder on that lead. And check our clearance again. Make sure the board seats. It does. One thing that is very useful in the in any lab, not just mine, is saving cuttings from components. These make amazing jumper wires, small stuff, anything like that. Wonderful to save cuttings. Once this jar gets full, I'll probably send them to recycle as opposed to save them, because I won't need more than that. At least I hope. Means I'm doing, actually, well, that would be good, because that means I'm doing quite a lot in the lab. The next capacitor we want to tackle is this is C4. And we'll just pull this out real quick. These are desoldering okay. The solder's not too old. Sometimes super old solder has a tendency to I got the wrong lead again, dang it. Very old solder has a tendency to be really hard to melt, especially in the get it to come apart. Yep. Polarity on these caps is very important because they get very cranky when put in circuit backwards. In this case, negative is the hash marks, at least going by what the other capacitor was. So we'll just pop this in here like so. And we'll get an iron. Oh, that was one of the IC pins. Oops. Don't want to overheat that. And that actually was connected to that surface mount cap, so we have to redo that solder bridge. Okay. Oh, that's just a tactile switch, so all the controls over on this side. Okay. Let me finish servicing this control, and then we'll put some power to it and see if it works before we put it all back together again. Okay, we have the Rigol on. This particular unit is center pin positive, so we do not have the reverse polarity dreaded problem. And we're going to go to 6 volts DC. And just because I don't want to completely destroy it, we'll go to 500 milliamps, not 3 amps. All right, we'll power it up. Well, the LED is on now. That is much better, much louder than before. So that's all the way up. Turn the we're drawing about a half a watt, so 60 milliamps off the power supply. Not bad. Given that's so much louder, though, I wonder if those caps were toast. Oh well, we can find that out. We'll do something crazy like start the SMU. And, oh look, I have alligator leads right here already, so that should make testing a lot easier. While the SMU warms up, we will put this back together. Have to be really careful putting this stuff back into plastic, especially plastic that's this old. It's really easy to shatter something accidentally. Yep, that hole's already stripped out, actually. All these white tabs that are falling apart. These guys right here. I couldn't figure out what these were. These are the locking and locating tabs around the unit. They're cracking off and falling out. And sticking to relatively everything. Okay, this does not want to go back in. That is, the board's laying correctly. That goes in that way. It is supposed to go under the speaker. Ah, there it goes. Okay. Just needed a bit of persuasion. Now I'm being really careful when these screws go in so we don't blow the holes apart. Self-tapping screws, especially into plastic without threaded inserts, are usually not good for too many cycles. That is much louder than it was before. Okay, so that's obviously working way better, even on batteries, than it was before. A little bit more cleaning. Keep finding places that are dirty on this knob. Let's check if these caps were leaky and if that was part of our problem. I have the source measure unit set up to supply me with 10 volts. Our polarity is correct. Force high is on the high side and force low is on the low side, so that is fine. And I've asked it for 100 milliamps, which is well inside the power envelope of the 2450. Well, that's not good. Let me show you what the source measure unit's doing. I apologize for the glare, but I do need a little bit of lights on in the lab. So what we've got is we have the source measure unit, source voltage measure current, which is correct. And then I have set it to 10 volts, which is what our capacitor is rated. And I've asked it for a current limit of 100 milliamps. So if the capacitor was good, we would see it charge up to 10 volts and then stop. And then there would be a moderately low leakage because nothing's perfect. The capacitor will have a very small leakage current running through it. Now, this is not set up for a high, extremely low current measurement because I should be using sense lines and also some guarding and shielding and things like that. But this is capable of reading down to 10 femtoamps. If I remember the spec sheet right, this is either point. Yeah, I think it's 10 FA is what this can measure to. So extremely sensitive unit, well within the capabilities. And 100 milliamps might as well be, if you can go down to 10 femtoamps, 100 milliamps is a ton. So we'll turn the output on, and we have 9.9994 volts, and we'll notice the current is starting to run away. So we have a milliamp going through the capacitor right now. There's no way that should be doing that. And now it's falling. So it was climbing for a little bit. So now this is soaking the dielectric of the capacitor, things like that. So it's one of the reasons why capacitors can hold their charge even after you've shorted them. And exceptionally large power capacitors, shorting bars are used and things like that. And they're stored with shorting bars on them because of dielectric absorption and a few other things. So this is falling. So this cap might be good, but a milliamp at 9 volts. But we're still at half. So 500 nanoamps. No, microamps. So we're at 500 microamps going through that electrolytic capacitor. Now that's generating a lot of heat and things like that in the capacitor. So I'm glad that one's out of there. Let's check the other one. Cap's kind of warm. Not awful, but it is noticeably warmer. 25 volts. Now this capacitor is rated to 25 volts. That is also within this power envelope, so we will actually be nice to this capacitor, and we'll set this to 20 volts. And then we'll say go. And we actually peaked out at current limit for a second, but that was because the cap was charging. But we're at 23 microamps and falling. So this smaller capacitor was probably still in good shape. That larger capacitor was definitely struggling. We'll let this soak. We'll let this soak at 20 volts and see how low we get. I'll bring you guys back in a little while. Well, it hasn't been very long, maybe about 5 minutes, and we're at 1.4 and still falling. So let's see how low we go. I'd love to get under a microamp. Let's start playing around with nanoamps. Come on, you can show me nanoamps. Let's go. Well, we got into the nanoamps. We're at 116 nanoamps. So now I'm at a point where the measurement setup is starting to influence the measurement. It's not going to go much further than this because I really need to now start using guard voltages and sense leads, and the 2-wire measurement is now pretty much at its limit. So that's about as good as we're going to get. So the larger cap was definitely struggling. This smaller cap is behaving quite well, actually. Well, yesterday is now today, and this thing performed well overnight. Everything was fine. Didn't hiccup. It was still running in the morning. No volume problems. The volume wasn't bouncing up and down. So I think we took care of the little noisemaker unit. For those that are following along and like this sort of thing, the capacitors I used were 220 microfarad, 35 volt radial. This was Panasonic. No particular reason why it was Panasonic. This was just the 220 mic that I had here in the lab. The 10 microfarads were Nishikon's, the UPW series. Very good, high quality capacitors. Not the cheapest things on the planet, but definitely worth picking up. So that's it for now. And as always, I will see everybody in the comments until the next video.